Good morning, all. Very welcome to a webinar on topology optimization. So, myself, Amal Raj, I'm a project engineer in CDAC, Hyderabad. So, about CDAC, CDAC is an autonomous body under Ministry of Electronics and Information Technology. So we are located at 12 different locations, and what CDAC mainly do, as the name suggests, advanced computing, Center for Development in Advanced Computing. So we mainly do research and development activities on advanced computing areas like IoT, ML, cybersecurity, blockchain, uh, robotics, RPA, autonomous navigation, ubiquitous computing, VLSI, quantum computing, etc. Okay, so also we as an organization are providing technical trainings as well. The main form of training which we provide are PG diplomas on different domains of 6 months. For that, you have to undergo through entrance examination, and according to that, you can get into different courses in different locations. Also, we are providing courses under FutureSkills Prime. Mostly a web-based course, a self-paced course, like you are aware of platforms like Coursera, Udemy, and all. Similarly, there are self-paced course which we provide, and which is called as bridge courses. And there are other courses for government officials as well, and there are workshops. We regularly conduct workshops as well. So anyway, that's about the organization. And about myself, I'm a project engineer in SITAC Hyderabad. I'm part of 3D PM team, 3D printing and additive manufacturing. Uh, uh, I have around 7 years of experience in additive manufacturing, that to mainly on the design domain. And there is a design technique called the DFARM, Design for Additive Manufacturing. So I have around 5 years experience in that as well. So before jumping into what topology optimization is, I want to discuss a little bit about manufacturing, and I'll discuss about additive manufacturing as well. And after that, we will discuss about the process chain involved in additive manufacturing. Then we'll go into topology optimization, right? Yeah. So we'll start the session. Okay. So topology optimization. Okay. So before jumping into what is additive manufacturing, first we have to know what is manufacturing. Okay. Manufacturing is the process of turning raw materials or parts into finished goods through the use of tools, human labor, machinery, and chemical processing. Okay. Following are the common manufacturing processes. Anyway, there are lot of manufacturing processes. I think all of you know what is the manufacturing process is. It is turning some raw material into a functionally useful material, like goods, you can say, with the help of a human labor or a machinery or some chemical processes or some tools and techniques. Okay, that is called manufacturing. So there are various manufacturing technologies available as of now, but in that, the commonly used manufacturing technology in case of mechanical domain are subtracting manufacturing, you can see, forming, casting, and the last one, additive manufacturing. Okay. Uh, so yeah, jumping into subtractive manufacturing, as the name suggests, subtractive manufacturing is a process by which 3D objects are constructed by successively subtracting or cutting a material away from a solid block of material. Okay. Examples are milling, turning, drilling, etc. So, as you know, it is one of the commonly used manufacturing process. You can see there will be a block of material, and from that we will carve out the excess material, and we'll get a final product, which is the functional part. Okay, and with that there will be a lot of waste materials also. Okay, so subtractive manufacturing is nothing but we will have a block of raw material. From that we will subtract out the excess part, and we will get the functional finished good. Okay, and there will be a lot of waste materials as well. So the next one is forming. Okay, forming is the process by which 3D objects are constructed through mechanical deformation. The workpiece is reshaped without adding or removing the material, and its mass remains unchanged. Okay, you can see forming is nothing but you have heard of sheet metal fabrication. That is one kind of forming process where the sheet metal will be of a definite mass, definite weight, everything, but we will bend that material or form that material into a desired shape without changing the mass or even the thickness or some parameters of that object itself. Okay, so for that there is a requirement of making specialized toolings. You can see this punch. So I'll annotate and show. This is a tool which is specially made for making. This is the raw material. You can see the flat plate is the raw material. In order to make the flat plate into a channel like this, we need a tool to be made in this shape. Okay, so that is called forming. But the forming, it is very limited of use. For an example, you can make cabinets, almirahs, wardrobes, and etc. Even enclosures using forming, but it is very limited to manufacturing because we don't have so much design freedom in case of forming. So, but anyhow, for a mass manufacturing perspective, it is very easy to manufacture using this process. Okay, so jumping into the next slide. So hope you all understood what forming is. The next one is casting. So the process by which 3D objects are constructed by pouring a liquid or molten material into a mold which contains a hollow cavity of the desired shape and then allowing to solidify. Okay, so I'll explain that. Casting is nothing but molding, and it is also known as molding. You have heard of injection molding and all. So it is nothing but there will be a molten material and it is poured into a cavity of a desired shape. Say if you are making a water bottle cap, there will be a cavity with the cap shape, and into that cavity we will pour the molten polymer, whatever it is being used, and we will allow them to solidify either by cooling or keeping, like there will be different processes. Sometime it will be chemical processes, sometime it will be cooling, forced cooling and all, like informal cooling is there. So using different kind of solidification processes methods, we will allow them to solidify and we will get the desired part. But the initial cost involved in case of casting or molding is too high because we have to make a tool out of subtractive manufacturing for a casting, for a tool and die to be made. Okay, this is actually the cast, sorry, the die which the cavity will be there, and that in order to make that die, there is say even for a small water bottle, the tooling cost required for making a water bottle is close to 2 to 3 lakh. You can a minimum I am saying. So it would be justifiable only if you are able to make mass number of parts, like thousands and 10,000s of parts, then only the mold price would be justifiable. Okay, so if you are making something in a least quantity, the mold is the sorry, casting is not actually casting or molding is not actually the right manufacturing process to approach. Okay, so next we'll in between, if anyone has any doubt, you can ask. Okay, you can always stop me and ask. Yeah, then moving to the next slide. The next one is additive manufacturing, also known as 3D printing. Okay, so the technical term is additive manufacturing, and 3D printing actually is the printing process, but anyway, it is commonly known as 3D printing in layman terms. Okay, so the process by which 3D objects are constructed by depositing raw material layer by layer with the help of an energy source and solidifying using a cooling source. So similar to casting only, there will be an energy source either it will melt or it will fuse the material. And after that, there will be a solidifying source which will cool the material. But here, so if I go back, you can see that in casting, this is the desired shape. The blue cap kind of a structure is the desired shape. The runner and the riser will have lot of wastage material. Okay, the runner and the riser will have lot of wastage materials. But in case of additive manufacturing, we will start with zero material. There will not be any raw material present. If you remember what I uh, explained about subtractive manufacturing. So in that, we need a block of material in the beginning itself. But here there will not, there will be only a build plate. Onto that, uh, material is being deposited, and it is either sintered or either melted, or there are a lot of processes involved in that. Anyway, I'll explain about a commonly used 3D printing technology called FDM, fused deposition modeling, and this is an example for that only. Anyway, before going into that, we will have a molten material and we will deposit that layer by layer, and this layer will be of, one layer will be of very minute dimension, say even 10 micron to up to, yeah, please. Okay. Yeah, 10 micron to around 400 micron, up to that level of layer heights are possible in case of a polymer FDM machine. Okay, so and it is printed, it is deposited layer by layer until we get the desired shape. So sometimes there will be some supports involved, but still the wastage of material is very less as compared to conventional and casting process. Okay. Yeah. So that is what additive manufacturing. It is a process by which 3D objects are created by depositing raw material layer by layer with the help of an energy source, and cooled by with a solidified with the help of a cooling source. Okay. So this is a typical FDM, fused deposition modeling machine. Here, the filament will be of wire form, and that filament is heated by a heating element. So if you see, this is the filament, it will be of a wire form. Okay, it will be like wire form, it will be in uh, cartridge wire, kind of a cartridge it will be, and there will be a heating element where it heats the wire, and the wire is being melted. That melted wire is deposited through the nozzle into a build plate uh, in a layer by layer fashion, and that layer will be of micron level thickness, and that layer will make the final part in FDM process. Okay, so the next one is classification of AM processes, like according to American Society of Testing and Materials. Okay, so if you see AM process, AM is nothing, additive manufacturing. It is an abbreviated term for additive manufacturing. There are 7 ASTM classifications for additive manufacturing. Anyway, I'm not going deep into that. So I'll just explain, like material extrusion is one of the most commonly used. So that was actually, this is a material extrusion process. In that, there is fused deposition modeling and fused filament fabrication. And the next one is VAT polymerization. This is the first 3D printed technology which was invented. And in what VAT polymerization, there is a SLA and there is DLP. And here the raw material will be of resin form, and the energy source will be either laser or light. And there is sheet lamination. This is actually an outdated technology. In that, the sheet metal is being cut and it is welded over one another, but it is very outdated technology. It is nowhere used as of now. And there is powder bed fusion. Here again, the raw material will be of powdered form, and the solidification source will be either an electron beam or a laser. And there is binder jetting. This is actually similar to FDM only, even binder jetting and material jetting. Here actually uh, material is actually in the form of binders, and here advantage is even binder jetting and material jetting, multi-material, composite material, and even multicolor materials are possible to print in binder jetting and metal jetting. And the last one is DED, called direct energy deposition. It's nothing but welding. You all know what welding is. So a precision, like a more high resolution welding guns are used to deposit material one layer over the another. Okay, anyway, I'm not going any deep into that. I think I'll explain where you can learn more about these technologies, that I'll explain in the end of the session. Going into the next slide, AM evolution. Just in 1984, as I said, SLA was VAT polymerization. In that one was SLA was the first technology. It was invented in 1984. Then the 86, the first 3D printer was patented. And 89, Stratasys, a company called Stratasys, created FDM machine, fused deposition modeling machine, which is one of the most commonly used type of 3D printing machine. Even it is available for 10,000 rupees also in all online platforms. And there is 3D system, and 3D system first commercialized one of their SLA machine, like stereolithography machine. They, again, Fraunhofer invented SLM machine, which is of which has powder as raw material. And then 2001, again, SLS, selective laser sintering machine, which is mainly used for polymers, was invented. And in 2002, a company called Arcam made EBM machine. And in 2010, a company called Organavo made first 3D printed blood vessel. And in 2013, a first 3D printed human, 3D printed human heart has been made. And in 2016, even mass production using 3D printed has been started. Okay. So there is a huge misconception that 3D printing is not suitable for mass manufacturing. Okay. But nowadays, considering the numbers of parts you have and considering the quantity of the part, even mass manufacturing can be obtained using 3D printing. And there is one thing called mass customization also. Anyway, like that is actually really deep. That is also possible in case of, only possible in case of additive manufacturing as a manufacturing solution. Okay. So the next one is AM process chain. So consider you have a 3D printer. What is the steps involved in making a 3D printed part? So the first one in that is generation of a CAD model. I hope all know what is a CAD design. CAD is a computer aided design. For that, you need to have a CAD software, or either you can download CAD models also if you in from different sites called Thingiverse, GrabCAD, and all. And you have to generate the CAD model first. That is the first step involved in AM process chain. So next, you have to convert that CAD model into a AM machine acceptable format. So the next one is conversion of that model into a AM machine acceptable format. For that, the first step involved is tessellation. Tessellation is nothing but conversion of that CAD model into triangular meshes, uh, which is mostly known as STL, or even STL file, .stl file, or OBJ files. These are all tessellated files. Okay, so first we have to convert that, and in that I'll show you how to do that also. In that you can control the resolution of the part which you are going to be printing. So all these things can be controlled over that, and after that there will be this tessellated file will be transferred to a next level of software called slicing software, where that software will slice the part into layer by layer according to the requirement, like according to the machine specification and your requirement, according to the print resolution you want, layer resolution you want. uh, the slicing software will cut the part into layer by layer fashion, and it will generate a G code for that, each layer actually. So usually 3D printer will have a manipulator. Either it will be a Cartesian manipulator, or Sometimes it will be a delta manipulator. Even nowadays, even articulated arms and SCARA robots are also used as a manipulator in case of 3D printing. So that is again a bit advanced domain called hybrid additive manufacturing. Okay, so in that, yeah, please. Okay. So the next one is machine setup. So once you have created the sliced file and created the G code file, next you have to transfer that G code into the machine 3D printer. That's it. Okay. So for that you have to do some machine setups like build plate calibration, material loading, even temperature calibrations, even nozzle changing and cleaning and all these things you have to do. So machine setup first we have to do. Then we have to feed the G code either through cloud, either through network, or even through a pen drive or a memory card or something like that. You have to transfer that G code to the machine, and the machine will even some machine will have automated calibration techniques, and some cheaper machines we have to do manual calibrations. So that is the next stage of AM process chain. And after that, once it is ready, everything is ready and good, then you can proceed the printing process, and the machine will start printing the part. And after printing the part, the process will be part removal. You have to remove the part from the build plate. For that, different type of techniques are used for different kind of technologies. So in case of FTM, you can directly take out the part. But in case of SLA, in case of SLM, even in case of electro beam building, there are several steps also involved in part removal. And there are some post processing steps. Anyway, I'll explain that. In case of powder bed fusion, you have to remove all the powder particles out of that printed model before getting the part out of what do you say, the build plate. So anyway, that is there. Then after that, the final process will be post processing. Post processing is nothing but removal of supports, and there will be, in case of FDM, mostly it will be removal of supports, finishing the part. Even sometime it may go to painting, uh, and even some heat treatment processes as well. But in case of SLA, in case of fat polymerization technology, SLA and DLP technology, you have to go for curing processes, and you have to expose the part to an ultra violet uh, rays, radiations, and then to that only the part is being cured, and you have to remove all the resins, and after that only you should do the support removal. Otherwise the strength of the part will be compromised. So similar to that, to different kind of technologies, additive manufacturing technologies, there are different steps involved in post processing. And after that, anyway, you can go for even again a step of subtractive manufacturing in order to change the fit and tolerances of the part. That is also possible, and now machines are available combinedly to do that thing called uh, what you say, combinedly to do that thing called hybrid additive manufacturing machines is also available. So yeah, anyway, before going into that, post processing, even finishing of the part using a sandpaper, sand blasting and all, even that is also part of post processing. Even painting of the part is also part of post processing. So anyway, topology optimization, we started the session with topology optimization. So with topology in AM process chain, topology optimization falls into the first step, generation of CAD model design. So what is CAD model design? So first we will go into that. What is CAD modeling? CAD is mainly used for detailed engineering of 3D models of 2D drawings of physical component, but it is also used throughout an engineering process, from conceptual design and layout of products through strength and dynamic analysis of assemblies to definition of manufacturing methods of components. So CAD is actually the basic basic requirement in order to make a functional part out of any manufacturing technology. Okay, so that is the basic item which is required using which we will make a functional part of any using any manufacturing technology, which I explain later. Even for subtractive, for casting, for forming, everything we need a CAD file. Either it will be 2D or for some cases even either it will be 3D or some cases even 2D is okay. Okay, so similar to that, you can see this is a CAD model which is made out of a software called SolidWorks. Okay, so we are here, we are using a software called SolidWorks. Okay, so the next one is once you have made a CAD model, the next thing you have to check whether the CAD model is capable of withstanding all the loads which is being applied to the model. Okay, so for that, there is a technology called FEA called or finite element analysis. Okay. So finite element analysis simulates the physical phenomena using mathematical numerical techniques by discretizing them into small elements. It is nothing but, see, this is a CAD model of a rectangular block. So, and there is a cylindrical block which is applying load to that rectangular beam. You can say that, right? So that rectangular beam is being discretized. That means it is being uh, divided into finite elements, like you can see finite parts, and each part is analyzed separately with respect to the impact which is having which is acted upon the part. Okay, so the cylinder is being inserting a force on this beam, and this beam is being exposed to what you say being exposed to that force, and that is being analyzed by discretizing that part into like finite parts. Okay, small elements you can say. Okay, so with that we can verify whether the part will hold the load or not, and which area has more stress concentration. In the part itself you can see the area here which is almost green has less force, and the area here it has more force acting upon the body. Okay, you can see that the color changes depicts, you can see from here also. Okay, so for that softwares are there, like even we are using SolidWorks, there are dedicated softwares like ANSYS and all are there for doing this kind of FEA activity. So topology optimization is something which is derived from FEA only. So jumping into topology optimization. Topology optimization uses FEA, that finite element analysis, to optimize the material layout within a given design space, that is topology, for a given set of loads, boundary conditions, constraints, with the goal of maximizing the performance of system. That means I already have a part. That part is being exposed to a simulation like FEA, and with the result of the FEA, we are eliminating the areas where stress concentration are less, which is done by the computer automatically, and we will get an optimized weight optimized part according to the boundary condition we have given. I'll show you one small example also how it is done using a software called SolidWorks. So I hope all of you understood what topology optimization is. Anyway, I'll jump into the software and I'll make a small part, small CAD model, and I'll show you how that topology optimization is being done. Okay. So before jumping into that, just a second, I'll switch to the software. This is a CAD software called SolidWorks. Okay, this is a CAD software called SolidWorks. So there are other CAD softwares also like Creo, even free CAD softwares are there like free CAD, and even limited license like 1 year or 2 year free CAD softwares are like there called Autodesk Fusion 360. You can use any kind of software, and there is even an online based CAD software called ThinkerCAD. Even that also you can use to make CAD models. But when it comes to simulation and topology optimization, and there is one more thing called generative design. So these are all advanced and more computation hungry things, and even a little bit complex to develop also. So these things are not available free of cost as of now. Okay. So here I'm going to make, anyway, I'm not going to explain CAD in detail. I'll just make a part and I'll show you. So here I am going to make a part, a small angle bracket. So if you see, there will be like those who are from engineering domain and all, they all know what engineering graphics is, sorry. And in that, all planes, vertical and horizontal planes and all. Similar to that, there will be planes in which you have to draw the part. So here I am going to make a part uh, first. So here I am going to make a sketch of the part. Okay. So you can see here I am going to make a sketch of the part. So this is an angle bracket. Okay. It has two clamps actually. So which is these holes are located for, say, for inserting some screws and clamping the part onto a wall. Okay. So I'll use that. So if you see, so I am giving dimensions to the part, like these dimensions are in millimeter. Okay. So I'm not going to explain all the steps involved in this. So for that, I'll later the session, I'll show you one course using which you can easily learn and develop the skill on CAD and all other activities. So I have made the 2D sketch. Now I am extruding that sketch into a 3D model. If you see, so I extruded that sketch into a 3D model. You can see that this is a 3D model of that part. Okay. So I am going to save the part. So here, one TO1, topology optimization 1 part, I am going to save the part. Now I save the part. The first thing I have to do is, as you all remember, I have to conduct a finite element analysis, as I discussed earlier, onto the part. Okay, I'll divide the part into finite elements and I'll conduct an analysis to the part. So I know the part. Sorry for the interruption. Yeah, the part actually is going into some field and it is being connected to some mechanical component, and it will have some force acting upon to it. Okay, so if you see here, I have the data of that force. What is the maximum force which is being acted onto the part? So for that, I am going to a tab called simulation, and I am clicking a new study, and I am creating a static study. That static analysis is called finite element analysis. Okay, so for that, if you see some components are there, here I have to assign a mechanical material property to the part. I have to like create fixtures. I have to uh, define the constraints and all. So first I am going to apply a material to the part. I'm sorry. So yeah, it might take a little bit time to load the material library. So all mechanical properties of the material, if you apply that material to the part, will be applied to the part, and even like compressive strength, tensile strength, the yield stress, Young's modulus, etc. Okay, so that too, CAD software material library will have even alloys, different grades of alloys also. Like in case of aluminum, one of the most commonly used alloy is 6061. So that's what I am going to use. If you see, the library is open now. Here I can see steel is there, iron is there, a lot of metals are there, even plastics are there, glass is there, carbon fiber is there. So when I'm clicking on the alloy, see, consider I want 6061 alloy of aluminum. So if you click on 6061 alloy of aluminum, you can see elastic modulus, Poisson's ratio, shear modulus, mass density, tensile strength, all parameters are listed here. Okay. So I am applying that material to my part. So you can see 6061 alloy is applied. Now I am going to fix the part. Sorry. I'm going to fix the part somewhere. Say, like whenever you are making something, it is going to be fixed somewhere, either onto a rigid body or through fasteners or something, or through bearing or through hinges, something like that. There will be some kind of fixture. So here I am going to use these two holes to fix my part onto the using a nut and bolt, you can say, and I'm clicking OK. And here I know that this you have to know whenever you are conducting a finite element study. Okay. I am going to apply a force onto the part. Okay. So I am going to apply a force onto the part of 500 Newton. Okay. I'm going to apply a force of 500 Newton onto the part. And that is done. The next part is mesh. This is where I explained converting the part into discrete small elements. Okay. Finite elements. Okay. Here I am going to create a mesh part. If you see, I am going to create a mesh out of it. So here there are actually advanced controls for mesh also, but anyway, I'm not going to explain that in detail. So I'm going to create a mesh of somewhere in between coarse and fine. So I am clicking OK. So if you see, now the parts has been cut into triangular meshes of small meshes. Okay. So now whenever I am running a study, a finite element analysis, it will analyze each and every part to the impact, to the impact on the load which is acted upon it, which is you can see on this direction. See, the arrow which shows is the load acting, and that load, how it will act on each finite element, it will analyze. Okay. Now I have completed the mesh also. Yeah. Anyone? Okay. I'll save. I'll save the part. Okay. And I am going to run the study. So here the study is being run. See, the study has been run, and now you can see the yield strength of the part is 5.5 into e raised to 7, but the maximum load acting upon the part is 3.7 into e raised to 6 only. So that means the system can withstand 500 Newton. Okay. The system can withstand 500 Newton. If the stresses acting upon to the body is more than the yield strength, then the part is going to fail. Okay. But even you can see it causes a little bit deflection. This is actually a little exaggerated version of that deflection. This much deflection won't be there onto the part once you once the force is acting. That also you can see displacement. The maximum displacement which is acting on the body is 8 into e raised to minus 3. That means 0.008 mm only. So, but it is little bit exaggerated in order to show that part. Okay. So you can see the stress acting onto the body and the area where maximum stress is there. You can see the part where it is being fixed is the area where maximum stress is there. And the part which is in the middle is where the minimum stresses are there. So now I got to know that my system, my part is not failing onto the load which I apply to that part. Okay. Now what I am going to do, I am going to optimize the part to reduce the material usage. Okay. So in case of additive manufacturing, lesser the material, lesser the printing cost. Okay. In case of subtractive manufacturing, lesser the material wastage, lesser the printing, lesser the manufacturing cost. Okay. If you have a block of material and if you're subtracting the part out of that material, if the wastage of material is less, mane the subtraction is less, then manufacturing cost will be less. But in case of additive manufacturing, it is ulta. If the weight of the material is less, then the manufacturing cost is less. Okay. So here I am going to optimize the weight of the part. So for that, again, I am going to copy the study. I'm going to copy the study to a topology study. You can see from here, topology study. Okay. So I'm clicking OK. And now it went to topology study. Now you can see, apart from previous static study, there are two more parameters. The first one is goal constraint. In that, I have one goal is actually best stiffness to waste ratio. Like whenever I am reducing the weight of the part, I want best stiffness. Stiffness is nothing but a resistance to deformation. Okay. So I want my part to be best stiffness. Even if I am reducing the weight, I want my part to be in best stiffness, so that even the load acting upon to the part will not create any issues onto the part. So I am creating best stiffness to weight ratio. And here mass constraint, I want to reduce up to 50% of the mass. Okay. Of whatever the part is. And even there are some manufacturing controls. These are all a little bit advanced anyway. I'm not going deep into that. So you can add preserve region. I am here going to add some preserve region. So I know these two holes are for screw mounting. So I have to give a depth of around 5 mm to that screw mounting. And I don't want to touch that area. Okay. So now that is done. Now if you see, already mesh is done. Now I am going to run the study. Okay. I am going to run the study. It is going to generate topologically optimized part. It might take a little time because it is a little computation heavy, topology optimization. So if anyone is interested to try out topology optimization, there is a software called Autodesk Fusion 360, but you have to buy cloud credits in order to access topology optimization. Actually, especially it is even if you don't have a powerful system, it will run the topology study on their cloud systems and give you the results. That is the advantage of Autodesk Fusion 360. Cloud computing, this is also an emerging technology. Anyway, I'll show you that. So in the meantime, if anyone has any queries, you can ask while the study is running. So it will actually, what happens, right? Whenever a finite element analysis is done, lot of iteration of studies will happen. Like one time, like hope you all remember these iterative processes, like where we will differentiate an equation and subject that to 0, and we'll try to find the solution. Again, we will iterate that so many times, and unless like up to a part where we get like equal or similar solutions. uh, Newton-Raphson iterative process is one of that. So it is one iterative process. So I think in mathematics you will be able to learn that. So yeah. So if you see, still it is taking a little bit time. So in the meantime, if anyone has any doubt, you can ask. Yeah, the study is run. Now you can see. See, this is the part. Lot of area, excess area where stress concentration is less, is being removed. Okay, you can see that, right? I'm going to save the part first. Previously our part was completely like this, and lot of areas where stress concentration is more is being reduced. So now what I am going to do is I am going to convert this part into a printable part. So now I am going to export the part into a smooth mesh. So new part file, and I am going to export that. Second. Then I am going to open that part. If you see part file, okay, I am going to export that part into a smooth mesh, new configuration. So if you see here, I don't know why it is taking a little bit time for that. Result export. TO1 to know configuration. Okay, anyway, I have one exported part with me. I'll open that. So now I have created an export smooth mesh out of it, and there is a slicing software called Cura. I'm going to open that slicing software, which is, as I explained, software which is used for generating G codes in order to communicate with the 3D printer machine. So Cura is an open source software. You can download and try it out. So here I am going to open the sliced part. So yeah. So if you see, yeah, see, this is the smooth part which is created out of the bigger part. You remember this is the fine. This was our model. See, so using topology optimization, we created that model into a smooth mesh like this. Okay, which we removed excess of the material and we were able to reduce the weight by 50%. Okay, this is how topology optimization is very much useful for weight optimization, and the advantage is that it can make use of capabilities of additive manufacturing, and uh, it is most suited for additive manufacturing, if you say. Okay, so that's it on the theory part. That's how topology optimization is being done. So anyway, if you want to learn more about topology optimization and even all technologies, capabilities, even CAD designed for additive manufacturing, there are some courses available in a portal called FutureSkills. Hello. Yeah, actually, I would like to show that if you see, there is a platform called FutureSkill Prime. I'll copy that and paste it into chat. There is a platform called FutureSkill Prime. In that, there are some courses available. If you see, if you click on courses. So before going into that, I'll explain a little bit about what FutureSkill Prime is. FutureSkill Prime is a joint venture by Ministry of Electronics and Information Technology and nasscom with Government of India for upskilling or reskilling existing manpower who all are in the industry or even in the teaching domain and everywhere, if you see them. So these courses are actually for people who want to upskill by themselves. Okay, so and it is, it will create a lot of job opportunities as well. So if you go into that, FutureSkill Prime is a skilling ecosystem focused on emerging technologies, powered by a partnership between MeitY, Ministry of Electronics and Information Technology, Government of India, nasscom, and the IT industry. It seeks propel India to become a global hub of talent in emerging technologies. So first I'll explain what are the emerging technologies. In that, if you see artificial intelligence, blockchain, 3D printing, which we discussed now, and if you see big data, cyber security, robotic process automation called RPA, it is software robotic automation, web and mobile development, cloud computing, Internet of Things, IoT, virtual reality, artificial, again, yeah, it came to artificial intelligence. These are the 10 emerging domains which the government of India found that the people need to be upskilled into. So for that, there are different courses available in the portal. Like if you see, uh, if I click on the courses tab, it will redirect into the course portal. So if you see, there are different courses available as part of that. So as I explained, for 3D printing, there are 2 courses available as of now. So I am going to search for 3D printing. If you see here, there is a course for introduction to 3D printing and CAD modeling, which will explain everything which I told in brief, in detail, in very much detail, which will make you an expert in CAD modeling, which will show you how DFAM, design for additive manufacturing, is done, and which will deep dive into topology optimization, generative design, reverse engineering, and all. And also it will show all 3D printing technologies and how to print a part at the end of the session. Okay, so the course is offered by combinedly by NAILIT, Calicut, and SITAC Hyderabad. It will be a 90-hour course. It is self-paced course. Once you register to the course, you can access the course for 90 days. Within 90 days, you will be able to complete the course. And it costs around 3,390 rupees with the GST. Once you complete the course, you are eligible for uh, digital incentive schemes by Government of India as well. So once you register, successfully complete the course, once you are certified, then you are eligible for half of the course fee to be reimbursed by Government of India. So effectively, the course fee will be hardly 2,000. Okay, so that is also there. If you jump into that, if you click on that, you can see you will jump into a portal. You can see that this is the course portal, and even you can click apply now in order to get into the course. And it covers all. If you see evaluation of 3D printing, various 3D printing technologies, uh, FDM in detail, like which I told you earlier. This is one of the most commonly used technology. And in module 2, there will be CAD modeling, and in that DFARM, topology optimization, everything will be there. In module 3, there will be advanced guidelines for DFARM and all, and even different print settings and how to use a printer. All these things will be explained. So this will be a very useful course for those who want to upskill themselves and those who want to reskill themselves. Okay, so I request all of you to go through the site and check whether in any of the domain, not even 3D printing, I'm seeing any of the 10 emerging domain. If you are interested in any course, you can always enroll to that course. And it is also a self-paced course, and you can look into that. Yeah, anyway, that's it for the session. So thank you all for joining to the session. Uh, in the meantime, if anyone has any doubt, I am 3D printing at the rate cdac.in. You can mail us in 3D printing at the rate cdac.in. And also for larger organizations, we are giving a spoke facility also for uh, being a partner to conduct this program. So those who are interested, they can contact us on that also. Uh, yeah, that's it for the session. In the meantime, if anyone has any queries, you can ask. Anyone has any queries? I think no one has any queries. So thank you all. Thank you for attending this webinar, and looking forward for you to go through the Future Skill Prime portal, and looking forward for some nominations for the program as well, for the 3D printing program as well. And you can also share these things among your colleagues and contact circle. Yeah, that's it for today. Thank you all. Thank you very much.